All right, we're going to compute a couple different arc lengths today, and they use somewhat different techniques. Now, the thing about arc lengths is once you set up the formula, sometimes you can actually integrate, and sometimes it's actually completely impossible. So usually the ones you can find the length of, it's going to feel artificial, the tricks, and if you haven't seen the trick, it's really, really hard to see. So I wanted to show you these two to show you one where it's pretty easy, and the other where it's kind of, if you don't know the trick, you won't be able to get it. So let's start with the first one. Apparently I left my chalk over here. No worries. All right, so the formula for the arc length is we're going to integrate, this time from 0 to 3, the function, which is going to be the square root of 1 plus, and we're going to take the derivative of f of x. F of x here is x to the 3 halves, which means f prime of x is going to be 3 halves of x to the 1 half. So that will become our derivative. So we're going to plug that into here. 3 halves x to the 1 half. And we're going to square this dx. And here's where things are actually kind of nice, because we're squaring, x to the 1 half just becomes x. So we get the integral from 0 to 3 of the square root of 1 plus 3x, 9x, over 4. So the 3 halves becomes 9 quarters. The x to the 1 half becomes x. And we're just doing this dx. And for this, we can do a straight up u substitution. We can let u be 9x over 4 plus 1. The order here doesn't matter. And so du will be 9/4 dx, which means dx will be 4/9 du. And now we can also compute the new bounds. So u of 0 is going to be, when I plug in 0 into here, I get 1. And then u of 3, when I plug in 3 into this, I get 27 over 4 plus 1. So the plus 1 becomes 4 over 4, so that'll be 31/4. And so this changes our integral to be the integral from 1 to 31/4 of the square root of u du. Not exactly. To replace dx gives me 4/9 du. So I have a 4/9 du to replace my dx. And now I have u's been replacing 1 plus 9x over 4. Dx gets replaced by 4/9 du, and the bounds get replaced. 0 gets replaced by 1, and 3 gets replaced by 31/4. And now we can just pull out the 4/9 in front, and we can integrate. So we have our 4/9. The antiderivative of u to the 1 half is going to become u to the 3 halves over 3 halves. And we're going to evaluate this from 1 to 31/4. And so now we just plug in. Plugging in isn't all that interesting, but we're just going to show the evaluation just so that our audience and our reader can know that we did everything correctly. So we're going to have a 4/9 in front. Inside my parenthesis, I'm going to put 31 over 4, and I'm going to raise it to the 3 halves. And I'm going to divide by 3 halves. And then I'm going to subtract when I plug in 1. 1 to the 3 halves is 1 divided by 3 halves. And that's fine. We're just going to leave it like this. To actually get a number here, we just plug it into a calculator, and it's going to give us some decimal approximation. So when you're doing these and you're computing the arc length, stopping right here is fine. You've shown me enough work. I know that from here it's just a calculator computation, but this gives me all the pieces that I need to find exactly how long the curve is. So this is for the easy ones. Let's look at the second one. The second one is actually harder. So let me erase this work. And now for the second piece, we're going to have g of x is going to be x squared over 8 minus the natural log of x, which means that g prime of x is going to be 2x over 8 minus 1 over x, which we can rewrite as x over 4 minus 1 over x. Okay, so the length of this curve will be the integral, this time from 1 to 2, of the square root of 1 plus g prime, which is going to be x over 4 minus 1/4 squared dx. Okay, and now this looks really, really bad because we can't really just do a u substitution. We don't really want to. Even if we did a u substitution on this, it would be super, super yucky because we'd have to do a trig substitution. This is where there's a really, really neat trick. If we actually multiply out what this expression is, x over 4 minus 1/4 squared, this is going to be x squared over 16 plus 1 over 16 minus twice x over 4 times 1/4. So this is just using the rule that a minus b squared is a squared plus b squared minus 2ab. This is a result from Algebra 1. But if you look at what this is, when we put these things together, you see that this term we get, we're going to get x squared over 16 plus 1 over 16 minus x over 8. Now, when we add 1 to this mess, what's going to happen is we're going to be able to cancel things pretty nicely. So let me show you exactly how this one works. Let me pause a second. I think I have a mistake. Oh, yeah. I see my mistake. So I had a typo. I put 1 over quarter. It shouldn't be 1 over quarter. It's 1 over x. So this is why I was getting confused. So let me change this to 1 over x. And so this becomes the following. We're going to have x squared over 16 plus 1 over x squared. And now we're going to have minus x twice x over 4 times 1 over x. And here you'll notice that the x's cancel, and we just have a minus 1/2. So this becomes x squared over 16 plus 1 over x squared minus 1/2. Now, this is actually really good, because when we add 1 to this expression, this negative 1/2 becomes a positive 1/2. And if this here were a positive 1/2, this could become a positive right here. That's the only difference, which makes this here exactly a positive. And in fact, that's exactly the case. We have 1 plus x over 4 minus 1 over x squared is actually equal, because of this, when we add 1 right here, I'll show you, x squared over 16 plus 1 over x squared plus 1/2. But when we put the plus 1/2, this here becomes a plus. So this is x squared over 16 plus 1 over x squared plus 2 times x over 4 times 1 over x. And this means that it becomes just the positive version of this. And so we get exactly x over 4 plus 1 over x being squared. This means that because this expression is this perfect square, when we square root, they all go away. And so this arc length becomes the integral from 1 to 2 of precisely this that has been square rooted, which is just x over 4 plus 1 over x dx. So this is a lot of work to see the very, very nice trick that by adding 1 to this negative 1/2, it becomes a positive 1/2, which lets us write it as a perfect square. And because this is now a perfect square, integrating this is easy. The integral of x over 4 is just going to be x squared over 8. The integral of 1 over x is the natural log of x. And we're evaluating this from 1 to 2. So now we just plug in. Plugging in, we're going to get 4 over 8 plus the natural log of 2 minus 1 over 8 plus 0. So that gives us a grand total of 3/8 plus the natural log of 2. This is the length of the curve g of x from 1 to 2. So I hope this lets you see this very, very specific trick that only ever works if adding 1 changes a negative 1/2 to a positive 1/2 in here. And there's a number of ways this can be set up, so look for this in the homework. I'm sure there's going to be at least one problem that uses this trick. So that ends the video for this week. I hope you enjoy the homework, and good luck on your exams and the finals. Bye.